So we're going to finish off with the complex number arithmetic by looking at the division of complex numbers. So let's say we have a complex number Z1, which is x1 plus I y1, and Z2, which is x2 plus I y2. We want to find the division or the quotients of these two. So what is Z1 divided by Z2? So at the top, we're going to have x1 plus I y1. At the bottom, we're going to have x2 plus I y2. Yeah, the way we solve this, or to simplify this, is very similar to what we had before with rationalizing the denominator. Remember, way back last year, we did the rational functions with the roots and all of that. Very similar. So we multiply by this thing called the conjugate. So what that means is wherever we have an I, we replace that with a minus I. So we'll look at that in much more detail later on. But the idea is whenever you hear the word conjugate, you replace I with minus I. Okay. So we're going to take this denominator, x plus iy, and replace that with minus I. Okay. Multiply top and bottom by the conjugate in the same way we do for rationalizing the denominator. So this will be x2 minus iy2 over x2 minus iy2. Yeah. Again, very similar to what we've done before with those rationalizing. Okay, so what's this going to be? At the top, we have a product, x1 plus iy1, x2 minus iy2 over x2 plus iy2, x2 minus iy2. Okay, so let's look at the top. What's that going to be? It will be x1, x2 minus I x1, y2 plus I x2, y1 plus y1, y2. All over, and then expanding out the bottom, very similar to what we did for the top, we're going to have x2 squared plus y2 squared. Okay, so what we can do now to simplify is put all of the real parts together into one term and all of the imaginary parts together into its own term. So we're going to have x1, x2 plus y1, y2. So those are the real parts over this denominator plus I, and then we can put all the imaginary parts together over that denominator. So that will be x2, y1 minus x1, y2 all over that same denominator we have there. x2 squared plus y2 squared. Okay, so here this will be the real parts, and this will be the imaginary parts. Okay, so very similar to what we did for the addition, subtraction, and the multiplication. Right. Any questions on how you solve these problems? Okay, so you multiply top and bottom by the conjugate, and then you have your real parts and your imaginary parts. Okay, let's have a look at an example. Okay, so we've got minus 1 plus 3i all over 2 plus 5i. Okay, so we've got this quotient of complex numbers. We want to find the real part and the imaginary part. So we look at the bottom. We've got 2 plus 5i. We find the conjugate, so replace I with minus I. So it will be 2 minus 5i. And then multiply the top and the bottom by that. So this is going to be multiplied by 2 minus 5i over 2 minus 5i. Okay, again, top and bottom, that is the conjugate of that denominator. Now we just simplify and then separate. So in the top, we have minus 1 plus 3i, 2 minus 5i, and then in the bottom, 2 plus 5i, 2 minus 5i. Okay, so let's have a look at the top. Normal distribution like we did last time. Minus the 1 times the 2, so minus 2, plus 5i, plus 6i, and then minus 15r squared, so that will be a plus 15. all over. What do we have at the bottom? That will be 4 plus 25. Okay, now we look at the real parts and the imaginary parts. So what are the real parts? That will be minus 2 and 15. We can put that together. That will be 13. The bottom, 25 and 4, that's just 29. And then the imaginary parts, we can put that together. So that will be the 6 and the 5. That will be 11. And then the bottom, same denominator, 29. Okay, and again, we've got the real parts. And we have the imaginary parts. All right. Any questions for this example? All good. Okay, so let's have a look at this conjugation property in some more detail. So the complex conjugates. Okay, so again, remember, complex conjugate is just replacing I with minus I. That's the only thing that you're doing. Okay, so no matter what you're given, whenever you have the conjugate or the complex conjugate, all you're doing is replacing I with minus I. Okay, now just some notation for this. Okay, if we have z is equal to x plus iy, then we write the conjugates in two ways. So the textbook uses the bar notation, so I'll write that. But if you're looking online or other textbooks, there's also the star notation. Okay, so just keep in mind those two notations. So the complex conjugates is given by z with a bar at the top, or you can write it as z with a star. Okay, you'll see those two notations for this. Okay, and again, all we do is we replace I with minus I. Okay, so you can write it as Z bar or Z star. You'll see both of those notations used as we go through. Okay, so let's have a look at some properties. Properties of the complex conjugates. With proofs. A lot of proofs coming up. Okay, so we'll go through the first proof slowly, and then the others I'll leave for you to do for home. Okay, so property number 1 is if we have z plus w being two complex numbers, and we do the conjugation of the sum, this is the same thing as doing z bar first plus w bar. Okay, so you can do the conjugation of the sum, or you can do the sum of the conjugations. It distributes over the plus. Okay, so let's have a look at a proof. Okay, let's say z is equal to x plus iy, and w, let's say, is a plus ib. All right, you can use whatever letters. Okay, that talking needs to stop. Okay, if I have to ask one more time, I'll leave and you can do this yourself. Okay, so we have z is x plus iy, w is a plus ib. We're going to substitute it into one of the sides. You can pick left side, right side, and you try get to the other side. So let's start by substituting into this left side, the z plus w bar, and try get to the other side. Okay, and then you can try do it the other way as well. Okay, so z plus w bar. So that's going to be the bar over the sum. So we're going to do that sum first. So that will be x plus iy plus a plus ib. Okay, and then the bar goes over everything still. Okay. And still here talking. Okay, so underneath the bar, we still have just a sum to do. We know how to do that. We add up the real parts and we add up the imaginary parts. Okay, so we can drop the brackets and we'll just have x plus I y plus a plus I b. Right, because we can just add up the real parts, the imaginary parts, the brackets don't really matter there. Now, what does it mean to do the complex conjugation? We replace I with minus I. So x, there's no I involved, so that just stays. IY will become minus IY. A, there's no I involved, so that's just A. And IB, that will become minus IB. Yeah. And again, we can look at this in terms of the real parts and the imaginary parts. So we've got x and minus IY, that's for the one complex number, the real and imaginary. And then A and minus IB, that's the real and imaginary for the other complex number. So if we treat them as two separate complex numbers with their real parts and their imaginary parts, what is that first one going to be? It's the conjugate, because the I is now been a minus I. So we can write this as Z bar. Yeah, and then the second one, that's the W bar. Yeah. Okay, very easy. Any questions for this proof? Okay, so you can try going the other way. So start with this right-hand side, substitute, and then try get to that left-hand side there. Okay, property number 2. We have ZW bar. So we have a product, and then the bar is over the whole product there. This is equal to Z bar times W bar. So it distributes over the plus. It also distributes over multiplication. And then the third one, if we have Z to the N bar, so some power of Z, and then we do the bar over everything. This is the same thing as Z bar first, and then we do the power. Okay, so these two are proof for homework. Okay, so it's exactly the same as number 1. You can let Z be x plus IY, W a plus IB, substitute into the one side, get to the other side. Okay, same thing for number 3. Any questions for the proofs? You're all good. Okay. Next is the modulus. Okay, so this is the third operation. So all of those arithmetic operations, we covered that before. Then the conjugation, that's another thing we can do to complex numbers. And finally, we have this thing called the modulus. So what is the modulus? So we write it as an absolute value notation. So 2 vertical lines, just like you do for absolute value. But inside is not a real number, it's a complex number. Okay, and this is defined as the root of x squared plus y squared. Okay, so we take x, which is the real part, we square it. We take y, which is the imaginary part, we square that. Take the root, and that is the modulus of the complex number. Okay, so please add these two to that list we started working on before the holiday. Okay, so we had that list with all the terminology with the complex numbers. We had the real part, the imaginary parts, all of that. Please add the conjugates and please add the modulus to that list. Yeah.
So when we like thinking the square of the cell, and like we just say why we don't see.
Yeah, so it's just y. Yeah. Okay. Any other questions on that? You're good. Okay, so please add those two to that terminology list we had before the holiday. Okay. We got another proof type question. Okay, prove that z times z bar is the modulus of z squared. Okay, so we're going to have quite a few of these proof type questions, especially for the class test and the exam. Okay, so it's like the short proof, so not like a whole 10 mark, it's a couple line proof, but there's quite a few of them. Okay, so we want to prove that z times z bar is the modulus of z squared. So we know what z bar is, we have that over here, and the modulus, we know what that is. So we're going to start from one side and try to get to that other side. Okay, and it's up to you which side we start with. Let's start on the left side. So that's going to be z bar. And we just substitute. So we know z can be written as x plus iy. So we can substitute z is x plus iy. So in place of z, we put x plus iy. And in place of z bar, that will be x minus iy. Okay, we expand this out. We're going to have x squared plus y squared, and those cross terms are going to cancel because we've got the minus sign. So this will just be x squared plus y squared. Now, if we look back a little bit, the modulus of z, that was the root of x squared plus y squared. Over here, we have x squared plus y squared with no roots. So this is just the modulus of z squared. Okay, because we don't have the root there. Okay, so you see what I mean? Just a few lines for the proofs. Okay, and this is the right-hand side. Okay, end of proof. Any questions? You're all good. Okay, so please expect something like this for the the quizzes, the tests, the exams, short proofs like this. Right. Any questions so far before we move on to the next chapter? You're all good. Okay. So next section, representations of complex numbers. Okay. So let's go right back to the beginning. What is a complex number? A complex number z can be written as some real number x plus I, we know what I is, the imaginary unit, times some imaginary part, y. So x and y are real numbers. You take the y, you multiply it by I, that gives you the imaginary part. Okay, so the real part and the imaginary part. Now notice, so we use x and y for a specific reason. We've got two independent variables, right? X and y, they can be whatever we want. Now, two independent variables, we can represent that in a Cartesian plane, right? Because we have x can be anything, y can be anything. They can both be whatever real numbers. So we can represent any complex number in this plane. This is not the Cartesian plane. There's no points, x, y points. This is the complex plane. So along the horizontal parts, we can write x as the real part of z. And along the vertical parts, we can put y as the imaginary parts of z. So any point here, okay, it's not a coordinate, it's not x comma y. That point over there is some complex number z, which is x plus iy. Okay, so you can pick any x, you can pick any y, that will give you some complex number. So here we have x, here we have y. So this is like the Cartesian representation of complex numbers.